This video is a continuation of the displacement, velocity, and acceleration lesson, and it covers the last two examples within that lesson. So let's take a look. It says the displacement in meters of an object from a reference point is given by this function right here. So this is our displacement function. Displacement is given in meters, time is in seconds, and it says when is the object moving towards the reference point. Okay, so what we should do here is we should recognize that, going back to our previous lesson here, when an object is moving towards a reference point, the product of the position function times the velocity function should be a negative number if it's moving towards the reference point. So let's go ahead and find our position function and our velocity function. Well, we have the position function right here, but what we could do to make our lives just slightly easier is we could actually just factor that position function. So I'm going to take that position function right here and I'm going to factor it. So I get t cubed and then t minus 4, right? That's its factored form. And then I'm going to find its velocity function. And the velocity function is just the first derivative of the position function. And I'm going to find the derivative in its unfactored form. So 4t cubed minus 12t squared, and then factor that, 4t squared, and then t minus 3. Again, recognizing that an object is moving towards the reference point when the product of the position function and the velocity function makes a negative number. Okay, so what we're going to do is, in order to find this, there's two ways that we can do this. The first way that we can do this is we can use a graph. So the first way, and I'll just put a little number 1 right there, is we can use a graph. And so what do I mean by use a graph? Well, let's graph this function s at t times v at t. Well, how do we graph the product of a function? Well, it's actually pretty straightforward. So we'll take s at t and we'll multiply it by v at t, and we'll use their factored form. So s at t is just this right here. And just to really prove the point, I'm just going to say, okay, s at t is this right here. Okay, and v at t is just this right here. Okay, there we go. So literally this is s at t times v at t. I just copied and pasted them and brought them down. Okay, let's clean this up a little bit. And so I will have 4t to the power of 5, then t minus 3, then t minus 4. Okay. And this right here is actually fairly straightforward because I can see that it is an odd degree function with a positive leading coefficient. Well, odd degree functions that have positive leading coefficients, they go from quad 3 to quad 1. Okay, what else do I know about this function? Well, I have its zeros as well. So sorry, I'll just scroll back up here. I'll write in the zeros. The zeros are as follows. The zeros are, okay, well, this function is equal to 0 when t is equal to 0, 0, 3, and 4. And this first 0 right here is a quintic 0. Okay. But these zeros here are linear zeros. So it's going to pass through linearly through these zeros, and it's going to pass quintically through this 0 right here. Okay, so all we have to do now is we have to graph this function. So it's an odd degree, positive leading coefficient going from Q3 to Q1 with these zeros. Okay, so let's just quickly sketch it out. Okay, I've got a 0 here. And I've got a 3 and 4, okay, and that's 0 right there. And I know I got to go from Q3 to Q1, okay, so I basically will go this way, and I'll pass quintically through this 0 right there. Well, what does a quintic pass-through look like? Well, it just really flattens out and then comes back up. And then it's got to pass linearly through 3 and linearly through 4. And as you can see, I'm preserving the Q3 to Q1 movement. Note that I'm not taking into consideration this portion of the graph right there because t cannot be less than 0. But what I need to find is I need to find when this function right here, the s at t times v at t function, is less than 0. Well, let's look at this graph. When is the s at t, v at t function less than 0? Well, between 3 and 4. So therefore I can say, therefore I'm moving toward reference point at, or between rather, 3 and 4 seconds. So we can say t right here is an element of 3, 4 circular brackets. So that's the first way we can do it. We can use a graph. The second way that we can do this is we can use a factor table. And this was something that we also covered in MHF or advanced functions. And so I'll show you the factor. I'll just put up the factor table method as well because it is exactly the same. It's just done in a different, mechanism of finding the answer. Okay, so this is the factor table right here. So my first factor is 4t to the power 5. My second factor is t minus 3. My third factor is t minus 4. And then I look at overall. Then along the top, I look at the zeros, noting that I never go below 0 because it's time. Time only goes in positive directions. So we have between 0 and 3, 3 and 4, and above 4. And I recall that in order to be moving towards reference point, it has to be negative. The product of the two functions have to be negative. So I'm looking for the negative value right here. And I find it is between 3 and 4. Speaking like candidly, my favorite method or my preferred method is the graphing method because I think it's slightly faster. But if you prefer the factor table, that also works. When is the object slowing down? Well, you know that the object is going to be slowing down. As we saw, if you go back to the previous, when the velocity function and the acceleration function have opposite signs. So when does velocity function times acceleration function, the product of those two equal a negative number? Okay, so the first thing that I'm going to do is I'm actually going to find the acceleration function. So I'm not sure why that was in green, but okay, acceleration function is the first derivative of the velocity function, and the first derivative of the velocity function is 12t squared minus 24t. You might be wondering how I got that. Well, I just go to the velocity function, okay, and my velocity function was right here. This is the easiest way to factor it, so I went ahead and, this is the easiest way not to factor it, but to find the first derivative. So I look at this velocity function right here, and I find the first derivative, and there's my first derivative right there, and then I factor it. And so I get 12t, and then t minus 2. Okay, and so what I need to do is I need to find when the velocity function times the acceleration function is a negative number. I'm going to take my velocity function, I'm going to multiply it by the acceleration function, and I'm going to use their factored forms. So the velocity function in its factored form is this right here. So again, just to prove the point, I'm going to take this velocity function, and I'm going to put it down here, and I'm going to put it right there, okay? And then I'm going to multiply that by the acceleration function, and the acceleration function is this function right here. Okay, so, oops. Well, that's not what I wanted to do. There we go. Okay, let me move this right here. Okay, so there we go. So there's my velocity function times the acceleration function. If I want to clean that up, I'm going to get 48 t cubed, t minus 2, t minus 3. All right, and again, my preference is to graph this and look at when the graph is a negative number. So I'll give you guys a second to try that out on your own. See if you can do this quickly. Look, you'll see that it is, in fact, odd degree again. And how do I know it's odd degree? Well, it's t cubed times t, so that would be overall t to the power 5. It's got a positive leading coefficient, right? And then I've got zeros at 0, 2, and 3. This one is a cubic, and these ones will be a linear. Okay, and I know I'm going from quad 3 to quad 1 because it's odd degree with a positive leading coefficient. So take a second, graph it, and see if you can come up with the answer. Okay, so this is what I have when I graph the function. It goes cubically through the 0, goes linearly through the 2, linearly through the 3, from quad 3 to quad 1. When is it a negative number? Well, it's a negative number between 2 and 3, so that means the object is slowing down between 2 and 3 seconds. Okay, moving on to the final example. For this final example, what I'll do is I'll let you pause the video and see if you can come up with the answers yourself, and then compare them with the answers that I'll post after I just talk through it. Okay, so the first, let's just first read through the example. It says the displacement in meters of an object from a reference point is given by this displacement function right here, where t is in seconds. So I've got meters and seconds. Determine when the object is moving away from the reference point. Okay, so recall if it's moving away from the reference point, your product of S and T and V and T should be a positive number. So moving away from the reference point, let's just double check that that's the case. Flipping back. Okay, moving away from the reference point, yep, S and T and V and T have to be a positive number. Again, our derivation of that from first principles is on this page right here. Okay, so let's go back to our question. Here we go. Okay, so I guess what we should do right here is we should find our displacement function, we should find our velocity function, and knowing like that I'm going to have to look at when the object is speeding up, why don't we just go ahead and find the acceleration function? Because all we're doing really here is just taking derivatives of the position function to find velocity, then taking the derivative of velocity to find acceleration. Okay, so let's go ahead and I'm going to write the position function right here, and that's t cubed minus 12t squared minus 36t. Pause the video and see if you can come up with, let's factor this actually first. S at t right here is equal to t, and then I get t squared minus 12t plus 36. And then S at t is going to be t and then t minus 6. Okay, and then here we go, velocity function is equal to the first derivative of the position function. Why don't you pause this now and see if you can find the first derivative of the position function. Again, finding the first derivative is most helpful using its unfactored form. Okay, and so here it is. The velocity function is given as 3t squared minus 24t plus 36, and then we go ahead and we factor, and we get this in its factored form. Like I said, since we're doing in part B, determine when the object is speeding up, it might be helpful just to take this velocity function right here and then take the first derivative, find the acceleration function. So we can go ahead and do that right there by saying that the acceleration function is simply equal to the first derivative of the velocity function. And pause the video and find the acceleration function. Okay, there it is. The acceleration function is given as this, 6t minus 24, and then in its factored form. Now you might be wondering, like, why am I putting these in factored forms? Like, why did I factor the first position function, and then why did I factor velocity and acceleration? Well, remember that if I want to find when an object is moving away from the reference point, I need to find S at t times V at t is less than 0, greater than 0, apologies. Okay, less than 0 was the previous example. So when is it greater than 0? So the easiest thing to do there is take the two functions, right, in their factored form and put them together. So let's take the position function, let's put that together with the velocity function in its factored form. And then once you have it in its factored form, it's actually pretty easy to simply, I think, in my opinion, to find the graph of that. I'll pause it and I'll let you see if you can try graphing it. The alternative is to do a factor table and find when it's overall positive. So take a second and use either method to determine when the object is moving away from the reference point. Okay, so I chose to do this as a graph. It's degree 5, so it's an odd degree function, which means, and it's got a positive leading coefficient, so it's going from Q3 to Q1. It has 3 zeros at 0, 2, and 6. 0 and 2 are linear zeros. As you can see, it passes through linearly, and 6 is cubic. So we're trying to find when it is moving away from the reference point, which means S at t times V at t has to be a positive number. And we can see when is it a positive number? Well, between 0 and 2, and then beyond 6 seconds. Okay, and so the object is moving away from the reference point from 0 to 2 seconds and after 6 seconds. Right, the next question says, when is the object speeding up? And the object is speeding up when the velocity function times the acceleration function have the same sign, which means that they would be a positive number. All right, so why don't you try pausing the video here, see if you can go through the whole solution on your own using either a factor table or the graphing method, and see if you can find the interval over which the object is speeding up. Okay, so you can see that I took the velocity function and then I multiplied that by the acceleration function, and then I combined the two functions together, and what I have right here is effectively I have a cubic function. So it's odd degree with a positive leading coefficient going from Q3 to Q1 with zeros at 2, 4, and 6, all of which are linear. Graphed it out. I need to find when is it positive. Well, it's positive between 2 and 4, and then it's also positive after 6 seconds. So I can come to my conclusion, which is that the object is speeding up between 2 and 4 seconds, and then after 6 seconds. Okay, so those are the last two examples of the acceleration, displacement, and velocity lesson. Thanks for watching, and I'll see you in the next one.